I continue my seventh block of my session, my lecture. Uh, in this block, we will discuss about the channel equalization in the wireless communication system. Okay. So there is two kind of filter. So I will go to introduce. So that is two important filter. That's zero forcing filter and minimum mean square error filter. So that's the two major filters that I'm going to introduce in the lecture. Before I go to the filter, I would like to introduce what is the purpose of the channel equalization. We know that is my previous lecture that we have a following important component is in a digital communication system. We are considered as a modulated signal. So actually, the modulated signal here, that's the signal that has been modulated and should be transmitted to the channel. And you need to have a transmitter filter at the transmitter in order to form the signal in a suitable form. And then this signals go to the channel, the correct channel. And other receiver, this signal should go to the equalization filter in order to reconstruct the signal. And in the mathematical description, we can describe the receiver signal is a convolution of the transmitter signal that has h of t, with the channel input response f of t, and with also the equalization filter the c of t. Yeah. So there is three components. Important component is a mathematical description of the receiver signal. Here, you have a channel. It's a channel convolution with a transmitter filter, and also with a convolution also with the input response of the equalization filter. Yeah. In for the linear filter, we expect that the equalization here should be the channel should be equalized by the equalization filter here. It means that if you want to obtain the receiver filter, which is equal to the transmitter signal, we underline that the filter should have this relation. It means that the convolution of the transmitter, the convolution of the channel with the transmitter filter, and also with the receiver equalization filter here should be a direct input. So that means that in all the time domain should be that is constant. And in the block structure, we can model that following. we have a transmitted signal here, we have a radio channel, and we have a receiver signal here, and the signal can be sampled by sampling something like a sample. It can be sampled before the equalization filter, or it can be sampled after the equalization filter here. And here is the equalization filter. We denote it as a CT, and we receive the signal that is set of T. Now each of T that transmitted signal, H of T that is channel impulse response, and the Y of T that is the receiver signal. Okay, now we introduce a method to implement the equalization filter by using the finite impulse response filter. Finite impulse response filter. That's the most convenient, important filter that digital filter that implemented by the digital signal processing that's the most popular. Besides the FIE filter, FIE that is finite impulse response filter. Yeah? And we have other filter that is infinite impulse response filter. So in the signal processing background, we know about these two important structure of filter. So it's an infinite impulse response filter. There's no recursive feedback. Yeah, there's no recursive feedback. And in this kind of structure, the filter, you want to design filter, you need to design the coefficient. And this coefficient of the filter, you need to design the coefficient. Yeah. So that's a general form of the finite impulse response filter. You need to design the coefficient. And even the coefficient can be fixed, or it can be additively updated. So if it is fixed, that is a normal filter, and if so, additively updated, then we call that additive filter. There is a very good book about this theory. I think that is additive filter from Haikin Simon. There is an additive filter book. Additive filter. I think that is Haikin also. You can search from Google. I think very good book. And to design the filter, it's very important to calculate the filter coefficient. And in this structure of the filter, you have 2n plus 1 tap. You have a 2n plus 1 tap. So that's one tap. That's one tap of the filter. Yeah. That's one tap of one filter. So you have a 2n plus 1 tap. And now we discuss how we can calculate the filter coefficient. to obtain the ideal filter for the channel equalization. Now we need to observe the receiver signal here. Yeah. So the receiver signal is the output of the filter. Receiver signal is as the output of the filter. You see here that is the output of the filter here, and that's the input of the filter here. And the output of the filter here is the output of the filter here is the convolution of the input of the filter with the filter coefficient. Okay, that's the convolution of the input filter with the filter coefficient. So now we just to we have this equation. We have the output of the filter. That's the output of the filter. That's the convolution of the input of the that's the input of the filter. Actually, the input of the filter here, that's the channel coefficient. In case that we transmit a signal, is the direct input signal. And here, that is the filter coefficient, and that is the convolution operation. That is the convolution of the input of the filter with the filter coefficient. So this one. Okay. And we observe for the n 2n plus 1 tab. We observe for the 2n plus 1 tab. Now we observe if suppose that m is equal to 0. Yeah. We suppose that m equal to 0, and replacing m equal to 0, replacing the m equal to 0 to this equation. I think it's not a little bit mathematic heavy, yeah. So you need to follow so that you can understand. So we have a set of 0 equal to 8 of 1 and n, and so on to the 8 minus n. Yeah. And we have a vector of the here the vector of the filter coefficient from c minus n to c plus n, and so on. And now we observe for the m equal to minus n here, m equal to minus n here, and we have a set of minus n is equal to the also the vector here. In the case that we observe for the m is equal to minus n. Yeah. So n is equal to minus n capital here, and here we observe for the n is from the plus n to the n to minus n. Yeah, and with this we have this equation. Yeah, we have this equation. So we can see that very actually it's a little bit mathematical, but it's not difficult because you just observe for the n equal to 0, n equal to minus n capital, and n equal to the plus n capital, and we have this following equation here. Okay. This following equation. And now we put together for the general equation, Then we have this equation. So in this case, you have output of the filter, and here we have a channel matrix, and that we have this coefficient filter. Yeah. You have the output of the filter is here. You have here is a channel matrix, and here you have a filter coefficient. Okay. Now we are writing is a magic form. So we have as the output of the set is the output, the vector output of the filter. S is a channel metric, and C is a filter coefficient. Yeah. So now you have a relation between the filter coefficient, C a vector, S is a metric, and Z is a vector of output of the filter. And it's also easy to calculate the filter coefficient by the inverse matching of the channel coefficient with the filter output. So it's a mathematical description of the filter, yeah, to calculate the filter. And this equation shows us the filter coefficient can be computed by the inverse matrix of the channel coefficient H formulated by this way, multiplied with the output vector of the filter. Because as you know that from beginning we should have this relation. It means that the conclusion of the channel here, I think this is not G, that is should be C, yeah, not G, is C. Okay, that is can you correct it instead of G? Could you write C? I'm wrong here, and here also C. That is the filter coefficient. So because we need to have an ideal filter, then you need to have this relation. It means that the correlation of the channel input response with the filter input response here, the channel input response. Could you correct here? See, the channel input response with the filter input response result is direct inputs. Or in the frequency domain, you have a multiplication of the channel transfer function with the filter transfer function is equal to the 1. Yeah, and we need to maintain this relation in order to obtain the ideal signal. So if you have the set of t is equal to the h of t. Yeah. So suppose that you have this relation, it means that you have a this relation. You mean you have the output set. So it means that you have the output that is direct inputs. So in this case, the set is the output, the convolution of the filter coefficient with the channel feed coefficient. That's a direct input. So in the discrete presentation here, so we have a set is a vector whereas center element is 1 and the other element is 0. Yeah, the center element is 1 and the other element is 0. So in this case, because we have an output that's a direct input, then in the discrete writing, then the element in the center is 1 and the other element is 0. So because the set is having this form, so the filter coefficient is the center column of the column. It's not of the set. I'm sorry, again this is wrong. The center column of the inverse channel matching. I think I correct for you now. It's not correct. Yeah. That is here. I correct it. That's not correct. Okay. Now, okay. So, I'm sorry. Because you know that so set vector have a this form. So the filter coefficient vector is the center column of the inverse matrix of the inverse matrix of the channel matrix. So we call this relation here. Relation. So we multiply by the channel matrix with set the output vector, because this matrix the set vector have this form. This form, then if you multiply with the inverse matrix, then it results in C is the middle column of the inverse channel matrix. It's the middle column of the inverse matrix. And I have a example. Now, but now it's a long time. I think it's handy for you to calculate. So I give you some example. I'm gonna explain. You can check it. You can check it when you are interested. How to calculate the filter here. Suppose that you have a channel input response like this. Even now you need to formulate the channel matrix. That's this concept. And then next you need to calculate the inverse matrix of the channel matrix. The inverse matrix of the channel matrix. And now we take the middle column of the inverse channel matrix. So that is the filter coefficient. And having the filter coefficient, you can develop the high input response filter like this. Yeah. Like this. And you know that this is a zero crossing filter that's very popular and applies to many systems. Yeah, it's very simple. It's simple filter. Okay. And is to ensure that you can recognize, you can reconstruct the signal. Yeah. To avoid multiplicative noise, or is to avoid the noise caused by the channel, by the propagation channel. Yeah. However, in this filter, you does not deal with the additive noise. Yeah. You do not deal with additive noise. So this filter does not have a function to reduce the noise. And if you actually that's the inverse filter, that is inverse operation. So you do the inverse operation, inverse operation, the inverse channel matrix. So if the channel is suffer from a heavy noise and the channel is having a low coefficient, yeah, so the channel is nearly zero. So inverse zero, a very small value. We have a trouble with the computation. Yeah. So if you do something with the matrix, then you do something inverse matrix, then you have a trouble with the calculation. So that is trouble of the zero crossing filter. So after afternoon, I will continue to introduce you as a middle mean square filter. This is also a very famous one, the optimal filter. Thank you for the attendance. Thank you. See you today afternoon, maybe again 40 past 1. Okay. See you afternoon. Okay. Moment ai với thầy giáo là mai mua ốp đem em. Mai mua ốp đem. Nay là mai mua ốp đem. Em em đợi tí thầy giáo phải thầy giáo gửi lại cái đi thầy trò mình đi em ơi. Thầy cho ta đi em. Có cái ông ấy mới em đi.
Bên Việt Nam thầy chỉ có mùa bảo vệ tốt nghiệp đại học. Bên này
cái số mà 22 kiểu 086 227 là số cố định đúng không?
Đồ 02 để cố định máy bàn.
Để máy bàn đúng không? Tôi đi em đi.